Hi, we have seen earlier that we can derive the temperature profile in a copper bar which is insulated by just setting up a heat balance. Well, in this example I will show you how we have used in principle the microbalance. So let's first make a drawing. Let's assume that we have here a temperature T1. We have a copper bar, and at the other side of the copper bar the temperature is T2. We have insulated this bar at two sides, so no heat is lost to the surroundings. So we have only conduction in that side because T1 is larger than T2. So the flow, the phi q in this case, will go in that direction of the lowest temperature. We know if we set up the thermal energy balance under steady state conditions, we get steady state, so no change in temperature. We got phi m, the mass flow rate, multiplied by the internal energy at the place in. But what was in? I didn't define anything what was in here. So let's assume that we look at two places between x and x plus dx. Then in is the place x. So in fact, we write down u at x minus u at x plus dx plus the phi q, which is going from x minus phi q at x plus dx plus the mass flow rate, well, the energy dissipation by friction. But in this case, there's no any flow, we only have conduction. So if we look at this equation, we see that phi m is 0. And we also see that phi m is 0 here. So the only thing which we leave out here is the balance of these two terms. So let's fill in these terms. Okay, what was phi q? Phi q was, according to Fourier's law, it was lambda multiplied by the surface area multiplied by the temperature gradient, and this all at the place x minus, well, the same equation at the place x plus dx and then you can see that in this case you could say, well, lambda is constant, the surface area is constant. Well, if this is all true, we can just divide all the terms by lambda multiplied by a, and then the only thing which is left then is minus dt dx minus x minus, minus dt dx at the place x plus dx. Then we could say if we divide this whole term by dx, we take the limit of dx goes to 0, we derive the following equation, the first derivative of dt dx. Here we have the equation from which we easily can calculate now the temperature distribution, because from this we get the temperature gradient dt dx is a constant, And secondly, t is a constant multiplied by x plus a second constant. Well, we have two boundary values because we know that at x is 0, t is t1, and we know at x is L at the end, t is t2. If you combine this all together, you get a temperature profile like T is, well, I have to look at it. At x is 0, T is T1. That means that K2 will be T1. So you could say that T minus T1 is equal to K1 multiplied by x. And now at x is L, T is T2. So if we divide it by TL minus T1, then this should be x over L. And you see that we get a linear temperature profile in this bar just by deriving from a microbalance. We can put all the formulas below. So here we see we have set up a balance between x and x plus dx. We put the normal, the energy balance. We have no flow, so the flow terms, the internal energy flows, and the energy dissipation as a result of friction flow is left. Then we leave out two terms, and these two terms represent the heat conduction in the copper bar which we consider. Subsequently, we set up this microbalance between x and x plus dx. We see that we assume that the lambda is constant. We assume that the surface area of the bar is constant. And then we get here an expression which can be derived easily to dividing by dx and the limit. Then we have in principle the definition of the first derivative of a function, and that's standing here. From here, it is just integration and going to the final result. You can imagine that you can do this also in a sphere and in a cylinder in a completely similar way. So you will see that in a number of exercises this is still the way to approach it. So a microbalance enables you to apply it to geometries you don't know, and that's the advantage. These are standard geometries, but you can also imagine that if it's more complex you can do it. Thanks for your attention.